Hello everyone, welcome. Let's start signals and systems with the introduction. So what are signals and what are systems? Signals give rise due to physical phenomena like a current in a circuit or the voltage across a capacitor or the velocity of a vehicle due to an applied force or the electrical signal generated out of a microphone due to the sound pressure that is received by the microphone and so on. So these are functions of an independent variable. So usually we call this independent variable time because we consider functions of a single variable in this course, but there can be situations where this function is actually a function of more than one variable. Now, for example, think about this situation where we consider the temperature variation at the different points of the atmosphere. So the temperature is a function of the location and the height that coordinate in the atmosphere. So some examples. So if we take a voltage source, Vs, and fix it to a capacitor resistor system, then there would be a current going through this, and there will be a voltage across this capacitor. This voltage will be a function of time, and that we consider as a signal. Also, if we think about a car moving along a road, then we can see due to this applied force, F, there would be a frictional force perpendicular to the velocity of the car, and the velocity of the car is a function of time. So you can see this is a signal. So once again, if you take a microphone and this microphone receives sound pressure and then it converts it to an electrical current, and that is a function of a single variable time. So all these are signals. Now these are actually called continuous time signals. So we will look at discrete time signals also. For example, the stock market index, if we plot with respect to the day, then it is a so-called discrete time signal, because given the day, which is an integer, you can tell the price and so on. So you can see there are many signals that give rise to physical phenomena, and there are systems that actually process these signals. For example, to this microphone, we may want to fix an amplifier so that the signal is amplified, and we may want to connect a speaker and once again convert that signal to a loud volume sound output, so that sound output itself is a signal. So this amplifier that does this amplification is a system, the speaker is a system, and so on. So you can see signals are functions of independent variables, and using systems we process those signals. Okay, so signals and systems find many applications in communications, automatic control, and they form the basis for signal processing, machine vision, and pattern recognition. So I mentioned machine vision and pattern recognition because these are new things that find many applications, particularly in these convolutional neural networks due to the convolution. And in this course, we will understand very well what convolution means. So electrical signals, voltages, currents in circuits, electromagnetic communication signals, acoustic signals, Images and video signals and biological signals are all examples of signals that we encounter. They are functions of independent variables and they carry information. So we define a system as a mathematical relationship between an input signal and an output signal. Now let's consider this amplifier, for example. Now let's think that this input signal is multiplied by 10 by this amplifier. So the mathematical relationship is multiplying the input signal by 10. So it is more complicated than that, but this is a very simple example of this amplifier. So we can use systems to analyze and modify signals. Signals and systems have brought about revolutionary changes. It would be a very interesting and exciting course. In this course, we will study the fundamentals of signals and systems. The types of signals in continuous time and discrete time, linear time invariant systems called LTI systems, Fourier analysis, Fourier series, Fourier transform, discrete time Fourier series, discrete time Fourier transform, sampling up to a certain extent, Laplace transform and Z transform, and stability of systems are the core components of this course. So the learning outcomes are these. After completing this course, you will be able to differentiate between continuous time and discrete time and digital signals and the techniques applicable to analyze each type. Apply appropriate theoretical principles to characterize the behavior of linear time invariant systems, namely the convolution. Use Fourier techniques to understand frequency domain characteristics of signals. That means we look at the signals in the so-called frequency domain. What are the frequencies that are contained in this signal? And due to processing of that signal, what happens to the frequency content and so on. So use appropriate theoretical principles for sampling and reconstructing analog signals, and then use Laplace transform and Z transform to treat a class of signals and systems broader than what Fourier techniques can handle. Okay, so what are the categories of signals? In this course, we study signals and systems that process these signals. So categories. So there are two main categories: continuous time signals, where the independent variable is continuous like time. So you can see this is the independent variable. And this is the signal. Xt is the signal. Then discrete time signals, where the independent variable n is an integer. So this is continuous. This is an integer. On the other hand, not only do we change the symbol for the independent variable, but we have parentheses for the continuous time signal, brackets for the discrete time signal. So there are some very strong similarities and also very important differences between discrete time signals and systems and continuous time signals and systems. So now let's think about the continuous time signals in little more detail. The independent variable time is continuous. Example, the sound pressure at a microphone as a function of time. It's a one-dimensional signal. So it's a function of a single variable, in other words. Image brightness as a function of two spatial variables. So this is actually a two-dimensional signal. Otherwise, this brightness of this image on the film we can describe as x st, for example. So there are two variables for the two axes. For convenience, we refer to the independent variable as time, because in this course we consider functions of a single variable. So here is an example of a speech signal. Actually, I captured that using a microphone and I'm plotting that. It is a continuous time signal. You can see it is a time axis. So in particular, at any point of time, if you ask me what is the value of this signal, at any point of time, let's call t naught, I can tell you the value of this signal at any point of time. So the time does not have to be an integer. It can be a real value. So this is a real value. So the film example. Now these are not actually digital images that we are talking about right now. It's an image on a film. So sometimes when you take large images, even now they use film cameras. So maybe you are taking a picture of 400 students standing to be taken, the picture to be taken on a film, and then you have the film loaded onto the camera, and then you open the camera lens and the image gets recorded on the film. So it's the x variable is continuous and the y variable is also continuous. So at any value of x and y, we can tell the brightness of the image on the film. It's a two-dimensional signal. Now, what are discrete time signals again? In discrete time signal, n is an integer. And we use brackets as I told before. So it is a function of an integer variable. Now takes on values at integer values of the argument of xn. Now take this for example. So independent variable is n. It is an integer. Xn is the value of the signal. So it is defined at 1, 2, 3, 4 and so on. So at 1 the value is 2. At 2 the value is minus 2. At 3 the value is 1 and so on. At minus 1 the value is 1. At minus 2 the value is 1.5. At 0 the value is 1.5. At 3 the minus 3 the value is 0.5 and so on. If you ask me what is the value of the signal as 1.7, I do not know. It is not defined. It is not defined. So therefore, the discrete time signal is defined only at integer values of the independent variable. Actually, the independent variable is an integer. So please remember that. Okay. Then what are digital signals? So you have encountered digital signals for sure. So it is actually a quantized discrete time signal. So for example, xnm, the signal can take only values from a finite set of values. What does that mean? So this is an integer. This is an integer. So this is a discrete time signal of two variables that we already understand. But is it digital? For it to be digital, the signal x can take only values from a finite set. Finite set. So for example, if you take a digital image, if you take my fundamentals of image processing and computer vision course, you will understand more about this next year. So it is a two-dimensional quantized discrete time signal. So if you take the values of the image, for example, let's take a 600 by 800 image. So therefore, n goes from 0 to 599, m goes from 0 to 799. The values of this signal at any location xm can be from 0 to 255 inclusive. It cannot be any other value than this because we represent these images as 8-bit images. So you can see that this is the finite set. This is the finite set. So if you have on the film, as we took in this example on the film, let's take this value at let's say 100 and let's say 140, this value. Assume that value turned out to be 94.6. But since we want to quantize it to the nearest integer available in this set, we would quantize it as 95. So this is from this set. So you can see the difference between a discrete time signal and a digital signal. A digital signal is a discrete time signal quantized. Okay. So now we will briefly look at systems. A system processes signals. So examples of systems, dynamics of an aircraft, an algorithm for analyzing financial and economic factors to predict bond prices, an algorithm for post-flight analysis of a space launch. Sometimes I have seen people when they fly unmanned aerial vehicles, UAVs, the flight details get recorded in an SD card on the aircraft, and when the aircraft lands, they would take the SD card and take the all the signals, wind speed, row, pitch, yaw, speed, throttle, and all these things, and do analysis on what happened. So you can see this analysis is a system. Simple systems, like we considered amplifiers as simple systems. And electrical circuit. So all these are examples of systems. An edge detection algorithm for medical images. So those are also systems. Even if you take an algorithm, that is a system. So there are two types of systems corresponding to the continuous time signals and discrete time signals. So this is a continuous time signal xt. You can see the independent variable is t. Also, we are using parentheses. The output is also continuous time signal, and this is a continuous time system. And if your input is a discrete time signal and the output is a discrete time signal, you will have a discrete time system. So there are other types of systems. We can categorize them into other categories as linear versus non-linear. Now, what are linear systems? Linear systems, actually, let's take a very good amplifier. Now, if the input voltage is 1 millivolt, let's say the output voltage is 1 volt. Okay. Now, if the input voltage is 10 millivolts, the output voltage should be 10 volts. If the input voltage is 100 millivolts, the output voltage should be 100 volts. So you can see the action of the amplifier is multiplication by 1000 irrespective of the input signal value. So you can draw this. Input versus output. Input versus output. So if the input is in millivolts and the output is in volts, so with the 1 volt you get 1 here, and with the 2 you get 2 here. So you can see that relationship is a linear relationship. It's a line. It's a linear relationship. So if we can represent the function of the amplifier as a multiplication by a scalar, as a very simple example, it's a linear system. But you know that the amplifiers actually cannot do this. So when the input is very large, this linearity would disappear. So the amplifier would saturate. So you can see it is non-linear. If you take the current across a diode, so when the diode voltage increases, you know that the current does not linearly increase. It is actually exponential relationship. Actually, it is like the coronavirus curve. So that's a non-linear device. But if you take a resistor and the current and the voltage, with respect to the voltage that we apply to the resistor, the current is linear. Can you see that? So now you see the difference between linear and nonlinear systems. And if you take linear systems, you have time invariant and time variant. So what is the meaning of this time variance? So what this means is, so if you take this amplifier, it does not matter whether you apply this 1 millivolt today, T equals T naught, or tomorrow, T equals some other time. It will be the same amplification. It will be the same amplification. So the system did not change with time. So it is time invariant. So there are time variant systems also. So I will give examples later on. And in nonlinear systems also, time invariant and time variant systems are there. In this course, we will study linear time invariant systems. So those are called LTI systems, or linear time invariant systems. So I think now you understand the different types of systems and what an LTI system is. Okay, then there are these system interconnections. These are also useful to know. We will encounter these things again and again later. To build more complex systems, we can interconnect system simpler by subsystems. So you can use that to modify the response of systems in amplifier design, stabilizing unstable systems and so on. You can use system interconnections. So these are some of them. The first one is a series connection. So you can see you take the output of this system and connect it to the input of the next system. So in the parallel connection, you take this output from this system, output from that system, and you add them here. And in feedback, a very important type of system interconnections, you take the output of this system and feed it back by multiplying by some constant to the input. To make system stable and so on, this kind of a thing is very important, the feedback systems. Okay. Now we need to understand the different domains. A very important part that we would cover in signals and system, the Fourier analysis. To understand Fourier analysis, we'll first understand what these two domains are. Now here I have drawn a signal with the independent variable time, and the signal itself is xt. It's a continuous time signal. Actually this signal is xt equals cos t plus 1.5 cos 2t. Simply if you take cos t, you will have a signal like this, right? I think we all know that. And I am adding another cosine with varies faster with time, multiplying that with 1.5. So this is the signal that you would get in this case. So we know that this signal changes with time. And if you take this signal, it changes faster with time. So the time it takes to complete one cycle is called the period. You know that. So how many periods are there per second? That is called the frequency, but we would like to write it as in radians per second. So that's called angular frequency, or the omega. Here you can see we have one signal at one frequency, let's say omega naught. Actually in this case omega naught is 1, and then another signal at 2 omega naught, because it is 2t. So we will study why these quantities are like this later on, but you can see that this signal comprises of two frequencies. Why do we have negative frequencies? We'll consider those things later. But right now what you need to understand is this time domain signal can be represented in the frequency domain or with the independent variable as omega with these kind of arrows, just indicating that at omega naught you have this kind of an amplitude in the cosine, and at 2 omega naught you have this kind of an amplitude in the cosine. So what you have here, this is the amplitude. So here it is 1. So to convert from this to this and from here to here, there are techniques. Those are Fourier techniques. So we will understand those techniques later. So you just need to know that there is this thing called frequency domain. Now, if you consider something like a piano, you hit the middle C, it generates some frequency. If you hit the middle C in the next octave, you generate a higher frequency, higher pitch. This is the meaning of these frequencies. Okay, so now let's look at a more general picture of this. Now let's think about this rectangle like signal. So this is the time axis. So this is this rectangle like signal. So you can see it has some ripples, but it looks like a square signal. Okay, so now as we did before, as we constructed this signal using two frequencies, we would be able to construct this signal using different sinusoids. So this is the main variation you can see that's there in this square signal. That's the main variation corresponding to the largest variation this square signal has, and then other variations. So but you can see this second sinusoid is of higher frequency than the first one. Actually it's twice, then the third sinusoid, the fourth sinusoid, and so on. But the amplitude of each of these small sinusoids becomes small and smaller. So we have drawn those the amplitude of the first sinusoid, amplitude of the second sinusoid. Amplitude means a height of the third sinusoid, fourth, fifth, and so on. But they are at different frequencies. So omega naught, 2 omega naught, 3 omega naught, and so on. These frequencies are there. So don't take these numbers to be literal. So they are multiples of omega naught, So these frequencies are there. So the addition of these different sinusoids give rise to this rectangular signal, and we can represent them with these heights of these sinusoids that we have drawn, and that is actually the frequency domain. Okay, so what we did today was understanding what signals are. They are actually functions of independent variables. We consider functions of just time or a single independent variables. Under signals we have continuous time signals, we denote them by xt, and discrete time signals where n is an integer and we use brackets to represent that. And then we understood systems process signals. So under systems we have linear versus nonlinear, and time invariant versus time variant. So if you take linear time invariant systems, we call them as LTI systems, and we study them in this course, the LTI systems. Then thirdly, we looked at the time domain versus frequency domain. Okay, from next time we will study signals in detail. We study how to plot cosines, how to plot exponentials, complex exponentials, and many other signals that we encounter in signals and systems, and other courses like control systems and stability of systems and electrical circuits and so on. Okay, thank you.